number 4, which of the following statement is true? Not true with regarding elements to the second period from lithium to fluorine. So this question is very straightforward. The only thing that you should know simply what is electron affinity, that is one, and what is oxidation state, and you know atomic radii, and what are reducing agents. Okay, so you have to find which statement is not true. So as I explained you in the previous class also, what is electron negativity and what is electron affinity. Electron negativity is the ability to pull electrons towards them. From lithium to fluorine, you have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So electron affinity means you are going to put an electron. So as I explained to you earlier in last time also, fluorine, when you consider about its electronic configuration, you will see to complete its octet, it needs one electron, which means it likes to get that electron and become stable. That is when the octet is completed. So basically, when the octet is completed, it is mostly like stable. But when you see along the elements, you can clearly see that fluorine will have the highest electron affinity to accept electron. That means it will accept the electron and it will give some energy out. Okay. So fluorine will have the highest negative. Why this is negative? Because you don't have to give energy to give an electron to fluorine, because fluorine needs an electron. But when you go to the second statement for beryllium, you know it is already in a stable state. So now you are going to put or break the stable configuration. So this will not be favored for beryllium. So which in return, you have to supply energy to break the stable configuration. That is why this will have a positive electron affinity. So identify the difference, both the affinities, but highest negative will be shown by fluorine because it is in the 7th group and it just need one electron. But if you go a little bit less element than fluorine, which will be, what is it? Oxygen, boron, carbon, oxygen, nitrogen. So all these, yeah, still they have some stability, but still they are not in the stable form. Fluorine needs only one. The other element before fluorine will need two. So in that case, you can imagine how much energy will be given out. Okay. Fluorine, since it needs only one electron, you can easily give, and the energy given out will be more negative. Okay. But the element before fluorine will need two electrons to get the stable configuration. Then first you need to add one electron. And remember, now you are adding the second electron to a negatively charged anion. So in that case, there will be electron-electron repulsion. Okay. So you need to understand. In that case, you need to give little energy more than fluorine, which means its negative value will be less. Okay. I hope this clears my idea. Okay, so the idea is, so lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So this needs only one electron to get stabilized. Like this is already stabilized. This is already stabilized. The idea here is this needs only one electron. So it will give a negative, large negative value. We will say EA is like minus 200 kilojoule per mole. But if you go towards oxygen, it needs 2 electrons, which means oxygen, when you add 1 electron, it will be O minus. Then O minus, if you add another electron, it will be O2 minus. Okay. But remember, here you are adding an electron to a neutral element. But here, for the second electron, you are adding the electron to a already negatively charged element, which in this case, remember, there is an electron-electron repulsion because it is already negatively charged, and you are going to put a negatively charged electron. So it will be a repulsion. So here, when you get the overall, the delta H electron affinity would be little less than this. So get the idea. Okay. So for the most cases in these elements, it is true that fluorine will have a highest negative value, but it will be highest. But here it will consume some energy for this electron-electron repulsion. Okay. That is why these all are negative. But the problem here is, here it is very easy. So it will have a more negative value. But here it is already stabilized. So you have to now provide energy to give an electron. Even this one will be little bit easier because this is as only 1 electron and you are going to put here to get the stable configuration. Okay. But remember, this will be, and this will be easier a little bit, but here you have more electrons, and here F minus will be more stable than lithium minus. You can imagine, this is a metal, this is a non-metal. Lithium mostly will be like to be in lithium plus than lithium minus. So in that case, this will have a highest energy that is given out. Okay. Okay, so moving on. So these two statements are correct. So then the other thing is highest oxidation state is exhibited by carbon. So this is very straightforward. You can clearly understand nitrogen have +5. If you get the most prominent oxide, nitrogen, you have N2O5. N2O5 is +5. Then you have N2O3 +3, N2O4, then NO2, N2O, NO, NH3, NH2OH. So from +5 to -3. You should know the oxidation state as well as an example for this oxidation state for nitrogen. So this statement is wrong because from lithium to fluorine, nitrogen can show +5. Okay. The atomic radii decreases from lithium to fluorine. That is correct because that is straightforward. Number of electron increases. Overall effective nuclear charge increases. The radius decreases. The ability to form cations, that is one part, and to act as reducing agent decreases from lithium to fluorine. First, we will check the ability to form cations. So you know, I told you now, explained you. Lithium, it does not like to be lithium minus and get stabilized because lithium is a metal. It likes to be in the stable form as lithium plus because when lithium plus is formed, an entire shell is removed. So in that case, you have to understand lithium is more likely to be in the lithium plus than lithium minus. Okay. But when you go across the period from lithium to beryllium, what do you think? Beryllium is already in the stable configuration. So do you think that beryllium likes to form beryllium 2 plus? No, it is already stable. So when you think only about these two elements, it will be clear lithium like to be lithium plus, beryllium likes to be in the same state. When you go, and when you finally come to F fluorine, fluorine is like to be as F minus by accepting an electron. So you can see lithium likes to be in cation form, beryllium likes to be in the same neutral form, fluorine likes to be in F minus. So you can see positive to neutral to negative, the formation of cation ability reduces. Okay. And the next thing is a reducing agent. What is a reducing agent? Reducing agent means it likes to get oxidized. The agent likes to get oxidized. Meanwhile, it reduces another compound. Okay. A compound which is named as reducing agent means it reduces someone. That is why it is a reducing agent. Lithium aluminum hydride is a reducing agent for a carboxylic or a ester. So what will happen to the for a carboxylic or ester? So what will happen to the carboxylic? It will be reduced to alcohol. Okay, that's the idea that you should get. So what will happen to the agent? It will like to get oxidized. So in principle, oxidation, in principle, forming cations. So it will be same as this. So it will decrease because you know lithium, it can easily oxidize. Okay, which means it can reduce something. Okay, but when you go towards the right hand side and up to fluorine, it likes to get reduced. So it should act as an oxidizing agent, not a reducing agent. So elements at the front end is mostly reducing agent. When you go across the period and up to fluorine, it will change. Okay, so I think this clears the idea. Okay, so moving on. So electronegativity, electron affinity, you should know. So nitrogen soil plus 5. And I have explained to you these two concepts. So you can see the electronegativity chart that is, this is given in your resource book. So this is according to Linus Pauling scale. But remember one thing, always remember one thing. Although these values that has given is corresponding to each and every element, okay, remember electronegativity is defined for bonding electrons, the ability of an atom to pull bonding electron. Okay, because if an element is alone, it cannot have an electron negativity because they have its own electron and that's all. But when you compare electronegativity, always remember, although it is specifically given for these elements, the values, electronegativity is compared when you have bonding electrons. For an example, if you have H, for an example, we say you have HCl, so hydrogen will be 2.1 and chlorine will be, where is chlorine? 3. So the electronegativity difference, you can get chlorine minus 2.1, 3 minus 2.1. So there is a higher electronegativity towards chlorine. So you can see there is an electron cloud shift toward this side. So it will be like delta negative this side, and it will be like delta positive this side. Okay. So that is how you measure the electronegativity difference.